Hello everyone, so now we are on our next video, aldehyde, ketones and carboxylic acid. We are talking about the chemical properties of aldehydes and ketones from MS Chauhan Elementary. So we were on question number 11. What is the question number 11 says? Which of the following compound is a hydrazone? What is hydrazone? Hydrazone is the compound which is formed by the reaction of an carbonyl group and basically aldehyde or ketone and hydrazine. So the molecule which I have taken right here is a hydrazine. Okay, this is your hydrazine. So it can be hydrazine or substituted hydrazine. Basically, not only hydrazine, any other substituted hydrazine will also work over here. Two hydrogens from hydrazine and oxygen from carbonyl group will go together when we are reacting the carbonyl with hydrazine. So loss of water molecule will take place. And CN double bond NH2 group will be formed. N double bond NH2, this group is called as hydrazone, which is your option number 4. This is your option number 4. Now come to question number 12. Question number 12 says the given compound can form an hemiacetal by reacting with itself in a solution. Which is the structure of this hemiacetal? So basically the compound given reacts with itself in the solution. Basically intra-reaction is what they're expecting. And they are asking which structure of hemiacetal it will form. So first of all, the compound is OH, CH2, 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 CHO. You have to understand that we have two groups over here. One is OH, in which oxygen can act as a nucleophile, whereas there is a CHO where carbon can have a delta positive charge and can get an attack from this nucleophile like a nucleophilic addition, and that will happen within the molecule itself because both species are present inside the molecule only. We do not need an external species here, external nucleophile to attack on this delta carbon. So when this attack will happen, this will go on the carbon and this is how the molecule will be formed. So oxygen will carry a positive charge and then there will be a hydrogen. There will be a bond cleavage between carbon and oxygen. O minus will be formed. Eventually, this hydrogen will be broken and this H plus, that means H plus transfer will happen. Why H plus transfer is happening? Basically, it's not H plus transfer. It's like your H plus is going out. This H plus is going out and attacking to the O minus. So when it is doing so, your molecule is becoming something like this. So here you have lone pair here, and OH. This is how your molecule will look like, which is nothing else but the cyclic hemiacetal. So this is the hemiacetal which will be formed, which is your option number B. So question number 13. What does the question number 13 says? Question number 13 says how many hydrogens are replaced by deuterium in the following reaction? So first of all, understand the compound which is given to us is ketone and the reaction is happening in the basic medium. Okay, so reaction means basically your ketone is present in the basic medium. So that means it is basically facing the tautomerism over here. It is going to do the tautomerism over here. And in tautomerism, what happens is your hydrogens which are alpha hydrogens or the deuteriums which are, or basically you can say the alpha carbon hydrogens are involved in the tautomerism. Okay, and when our solution, if you see, it is a D2O. So D2O means deuterium will be generated here. So that deuterium D plus is gonna be replaced. It's gonna take the position of hydrogen, which is alpha hydrogen's position. Okay, now how does that happen? Let's understand. Let me give you the shortcut first how to get the answer. So basically check how many alpha hydrogens we have. We have 1 over here and 2 over here. So these are the number of alpha hydrogens. These are the ones which are going to get replaced by deuterium. Now how does that happen exactly? That we will understand. So this is your base catalyzed tautomerism in which OH minus can act as a nucleophile and can also act like a base. Okay, now the behavior of OH minus acting as a base is gonna be the first if I have an acidic hydrogen. So if you see hydrogen over here, that is your alpha hydrogen. This is acidic in nature because of the presence of a minus M group, or you can say minus I group. So because of the presence of minus M minus I group, this alpha carbon's hydrogen is acidic and hence will be taken away by OH minus and loss of water molecule will take place. So how your molecule will eventually gonna look like? It is gonna look like as it will be R1 C minus R2 C double bond O and R3. So if you see here, this electron density can move over here and this can move over here and your species can look like this. So this is the resonating structure 1 and this is your resonating structure 2. Okay, and this is more stable form also with respect to C minus. So it will be R1 C R2 and there will be a double bond formation in the middle and CO minus will be formed. Now this O minus can now stabilize itself by two ways, either by taking hydrogen from the water which is generated over here. ठीक है, तो उसमें से it will take hydrogen. If it will do so, I think I've done a mistake over here. I have attacked O to O minus. I need to correct that. So basically this O minus is, the hydrogen is gonna react with this O minus, and eventually what you're gonna generate is OH, R3, R1, R2 and OH minus back. So in a basic medium, basic molecule OH minus catalyzes the reaction by converting your ketone to the enolate ion form. This is your enolate ion. Okay, and then that enolate ion again takes the hydrogen from the H2O and eventually forms the OH. Basically enol it forms and OH minus comes back. So this is your base catalyzed tautomerism. Now understand, instead of H2O present in the solution, if I have D2O present and H2O is released from the molecule, then what will happen? The H2O which is released from the reaction, and this H can go. Let's suppose if I have a water molecule along with H2O, this D can also go there and do the reaction. So basically your deuterium can form R2, C double bond C, OD, R1 and R3. This is what it will be forming, and it will be generating OD minus. So that's what exactly they're asking. How many alpha carbon? Now in this question which I had given you, the question was, you had the alpha hydrogens over here, but the reaction was happening with D2O and OD minus. So in that case, this hydrogen would have gone out forming HOD. Okay, and because D2O is also present, it would have formed the enolate ion of this kind. Just see here, this kind of enolate ion would have formed, or the other, if these hydrogens are getting removed. And then it has options. It can take the hydrogen from this HOD, or it can take deuterium from D2O, and it can form something like this. So basically now it can again tautomerize and form the same molecule back, D here, double bond O and H and H. So when you are doing so, I know it has become quite messy. So this is a reversible reaction. All this is reversible reaction. So here, when the reaction is happening, when again your molecule is going to attack on the enolate ion, what is going to happen is your hydrogen of H2O or DOH or D2O, whatever is there, the one of the hydrogen or deuterium is going to get consumed, and that's exactly what they're asking. Now once this forms this enolate ion and then it forms enol, again it can go through the same process, same reaction, and it can convert itself back into this, and this hydrogen will be back here. So this hydrogen will be back here, double bond here, through again the process of this base catalyzed tautomerism. So all these reactions which we are doing are reversible reactions. So in this case, the hydrogen is coming because we had a hydrogen over here. What if I had an OD over here? If I would have an OD over here, then the thing which would be coming on this carbon, alpha carbon back, would be deuterium. So that's exactly what they're asking. Ki how many hydrogens can be replaced by deuterium in the process of base catalyzed tautomerism? It will depend upon how many alpha hydrogens we have. Those many alpha hydrogens will participate in the base catalyzed tautomerism, and those will get eventually replaced by the deuterium also. So there are 3 alpha hydrogens. So 3 alpha hydrogens can be replaced by 3 deuteriums from the solution. Now question number 14. In question number 14, we have been given a ketone and we have been asked how many moles of PCl5 and NaNH2 would be required to convert it into respective alkyne. So we have to find out the sum of X plus Y. So first of all, so this is the ketone given. Now if you apply PCl5 on it, then what will happen? You will get 2 chlorines at the place of oxygen. So basically your oxygen will be out and 2 chlorines will be in, and POCl3 as a byproduct will be formed. Then every NaNH2 used, there will be an beta elimination, and 1 chlorine and 1 hydrogen, beta hydrogen, will be removed. So I have 2 chlorines over here, 2 beta hydrogens, both will be removed, and alkyne will be formed by using 2 moles of NaNH2. So 1 mole of PCl5 and 2 moles of NaNH2 will give you the total of 3. So X is equal to 3, which is your option B. Now question number 15 says pH MgBr, phenyl magnesium bromide, act as a nucleophile with. There are different compounds given. We have to understand it will act as a nucleophile only where you have a delta positive carbon instead of hydrogen. So if you have acidic hydrogen, then it will start acting as base. Okay, so acting as a nucleophile, it would require either the leaving group attached on the carbon, which is a delta positive charge, or you should have carbon with double bond O with a delta positive charge, or double bond anything, not just double bond O, any electronegative atom with carbon double bond and carbon must have a delta positive. So if this kind of arrangement is there, then only phenyl magnesium bromide may pH delta minus can act as a nucleophile. Okay, pH minus in fact can act as a nucleophile. So which of such compounds is there? If I talk about CH3SH, which is the first molecule, it has an acidic hydrogen, so here it cannot act like a nucleophile. CH3C triple bond CH, that is again terminal alkynes. Terminal alkynes, acidic hydrogen is there, so it will act like a base. Come to CH3COOH, again I have acidic hydrogen, it will act like a base. Only thing which is left is aldehyde HCOH. So there is a delta positive carbon over here. This phenyl will act as a nucleophile, will attack over here because there is the hydrogens which are present are not acidic in nature, so it will be acting like a nucleophile. Now come to question number 16. In question number 16, we have been asked find the correct order of reactivity of carbonyl compounds with LiAlH4. The first thing which you need to understand is LiAlH4 generates H minus, okay, and it can act as a nucleophile and it can attack on the specific compounds, okay, wherever the carbon has a delta positive charge. So basically here the attack of this H minus will depend upon how strong your carbon delta positive is. So we have 4 groups, A, B, C, D, and we have first group as ester. Ester is RC, RO, C double bond O, and then this. So here your carbon delta positive is getting a donation through plus M of RO, plus M of RO. Okay, you talk about ketone group, there is a plus I from both the sides. You talk about aldehyde, it has a R group, it has plus I from one side. So basically delta plus is highest in case of aldehyde so far, then it is decreasing when you talk about ketone, then it is decreasing if you talk about ester. If you talk about COCl, in that case I have a group which can give you minus I. If I just consider R everywhere and do not consider the effects of R here, then plus M, plus I, no minus I, no minus M, no plus I, no plus M, because hydrogen will not do anything. Chlorine will do minus I. Okay, so chlorine is a withdrawing group, hence delta positive will be highest over here, and hence the reactivity of H minus will be fastest over here. Hence reactivity of LiLH will be faster in the case of acid halides. So answer should be B according to this order. Now come to question number 17. In question number 17, they're asking which type of mechanism is being followed in this reactions. Just now we have discussed this. My LiLH4 generates H minus. H minus acts as a nucleophile and can attack on carbon with delta positive. So it is going to attack over here. This attack will cause the formation of O minus like this, and then eventually H plus, which is given in the mechanism, will get added over here, forming the molecule like this. So alcohol will be formed. So nucleophile is getting added in the RDS, and then the electrophile is coming and neutralizing the molecule. This reaction is a nucleophilic addition reaction. Now come to question number 18. In question number 18, we have what are the major products of the following reaction. The reaction has been given where we have a 1 mole of Grignard reagent, alcohol on a molecule, and CHO both together. So when I talk about CHO mean nucleophilic addition can happen using Grignard. Here acid base. Only 1 mole of Grignard is given. Then we will see which reaction is faster. Definitely acid base reaction is faster. Hence CH3MgBr will go and react with OH rather than attacking with CHO. An acid base reaction will take place and CH4MgBrH MgBr OCH2CHO will be formed. This will be your side product. So though both the functional groups can do the reaction, but OH will do faster because acid base reaction is the fastest. Now come to question number 19. In the question number 19, they have asked which of the following reagents does not form alcohol from aldehyde as given below. So in this question, we have been given the aldehyde, and we have to find the alcohol being formed. If I talk about LiLH4, it can convert my aldehyde to respective alcohol. NaBH4 can also convert. H2 with platinum and nickel can also do. The only thing which cannot convert your aldehyde to alcohol, it seems, out of these all 4. See, A is hydrogen with platinum, E is hydrogen and nickel. Both are capable of converting aldehyde to respective alcohol. So the only thing about which we have not spoken yet is Ag2O with NH3. So this is the one which cannot reduce your aldehyde to respective alcohol. So your option is D. Now question number 20. In question number 20, they says which of the following compound can undergo nucleophilic addition reaction with RMGBr. So RMGBr may R minus gets generated, which can act as a nucleophile as well as base both. If I take the compound, the first one, it is a ketone. In this ketone, if R minus is attacking, there is a delta positive charge over here. The R minus will attack on the carbon, oxygen will become O minus. So this is your nucleophilic addition. Now they are asking about the B. In B, R minus will attack, O minus will get the charge, then O minus will attack back and chlorine will be out. So it will form the respective ketone first, and this reaction is called as SN2TH. Chlorine will act as a leaving group over here. In CH3Cl, R minus, it is simple nucleophilic substitution. R minus will attack, chlorine will be out, CH3R will be formed. And on alkenes, the reaction will not take place. The only reaction where you can see nucleophilic addition is happening is your A.